Nope. There, are you getting audio now? Jeez. I need to solve this problem for next time. I'm sorry, that is like 2 weeks in a row. Thank you for pointing that out, Randy, and thank you for coming to the stream. I have talked so much, and there's going to be no audio on that first like half an hour. That is brutal. I feel like a fool. Some of this has to do with my new desk setup. Like I got rid of some of the old things, and I have fewer connectors now. But my microphone is the one orphaned connector to switch between my work machine and my my personal machine. That's brutal. Okay, so I did a whole long spiel about why we need to scan the database and the problems we're going to encounter. And it was just lost. So I'm going to keep this really brief. We want to iterate over all things in the database. There's a potential, because Rust has external iterators, that you could be scanning the database and inserting new values or deleting them at the same time. So for safety, we are going to hard link the files that at the time of when you request the scan, we're going to hard link all the files in the database, and then we can scan over those safely without them being removed from underneath us. So, cool. That's where we are. And so I was talking about, we created a test that is basically like what we want our interface to be. And then we created the interface function, interface method. Right now it does empty. And I think that we can pop this another layer and go just return none here. And we will fix this. And we're going to say create scanner. Now this is not what we'll do eventually. Let's actually just go ahead and turn that into a use. And before we go any farther, I'm going to do impl scanner new, and then we're going to return self, and then we will just figure out what needs to be the arguments here as we go. So then it's more like scanner new, and apparently I need to make that pub. Now this module is not exported in the crates interface, so I'm not worried about it leaking, which is why I can just do pub and not pub crate. Okay, so we're kind of building this top down. I sometimes go bottom up on these things because they're difficult to conceptualize, but I think this one, we need to do a bunch of stuff here. So we need to make something that's similar to the level scan. And we need to, or similar to a level, we need something that just contains the nursery data, because we don't care about writing to any of it. And then that's what we can build our holistic ginormous iterator on top of. So let's keep it simple, and let's keep this as self-contained as possible. And I think that what we want to do is we'll do impl as ref path. Okay, so this will be similar to like this level just takes path and level, but what we're going to do is scan the path for all the files that we care about, and hard link them. So there's one additional challenge in here, which is going to be we have the possibility that someone could want to scan the database twice at the same time or more than once. So we're going to have to uniquely identify the version of the iteration. Maybe we can punt on that at first, but I think like for safety, and maybe we'll make a test for it, like, hey, you can scan it twice at the same time, without having any sort of safety issues. Okay. All right, so we need to figure out, we're going to need a nursery. And honestly, I feel like this could just be an iterator over... Let me think about that. Because we need a... We need the original nursery, but what I actually want is the iterator over it. Not the original nursery. We need the original nursery data. So we're just going to get an iterator over this. But we need a copy because this nursery owns this B-tree map. We can't just make an iterator over it, especially if the nursery is going to be taking inserts. Now we could potentially look at what the safety concerns are, or what the safety guarantees are on a B-tree maps iterator. Because if we're going to take the position that the files on disk are immutable, we need to not have different semantics for the in-memory data, right? Okay, so yeah, I think it's not going to be safe to just return an iterator over this because there will be aliasing. Okay. All right, let's not solve the nursery thing here, but let's just pretend that we're going to use it. And we'll put, let's just say pub. Pub. We'll put a nursery data in here. Okay, and its value type is going to be this is interesting. We actually need a reference to the nursery. Okay, and we're going to need another method on there as well. Let's just generate a getter method. Okay. Okay, so we're just going to clone that. that'll be our copy of the nursery data at that time. And now we need to go through I'll make this down below as well. We need a kind of way to represent level scans. So let's make a level scanner. And then we'll figure out what goes in here in a minute. But what we want to do is excuse me. I think we can loop over all the files. The other option is that we could say, rather than looping over all the files with this path thing, we have the level itself create a scanner. So like say, hey, I want to scan the level. Because we don't care about the merger, we just care about going to the trees. See if it, yeah, and it has a file. It's honestly like similar to this more than the individual trees. Okay. Yeah, I think that's what I'd like to do. So obviously here we need to pass it. We're not going to do this. I think what we're going to do is we're going to pass the nursery, and we're going to pass the levels. Level. I'm sorry, that's going to be a slice. Okay, and then in our database we need to pass self.nursery and self.levels. Okay. So for the nursery, we clone the internal B tree, and we hold on to that. For the levels, we need to create we need to figure out what this is. And I think this is just Vec, a level scanner. But we need to figure out how to create this level scanner. Okay. We don't need path. And here, let's place qualified path with use. Oh. Same thing. Okay. And I think what we want here is the level scanner to implement iterator. Yeah. And it's going to have the same stuff as this, right? We'll implement next for it. And then what we can do potentially is have Yeah, I think we're going to wrap this in Peekable. You know, what's interesting is the nursery, not the nursery, I'm sorry, the merger uses this Peekable tree entry iterator. But this tree entry iterator, it just clones the tree, and then it has various iterators over each of the blocks. Right, so this entry iterator, right, just consumes, yeah. Okay. There's probably a similar pattern here that we can follow. So let's go tree entry iterator. Right, so each block gives back an entry iterator. So it starts at the root block. Right, and this is actually, you know, kind of a stack pushing type thing. So it's not exactly the same thing, but we will want to do something similar, I think. Yeah. Now we might have something like, you know, keeping track of the last key. Such that we can go through the nursery and the levels that we're scanning and skip things that are not hmm. Yeah, this logic is going to be complicated. But I think what we should do is start with being able to create this level scanner. So maybe what we need is from the level a list of the files that it has that need to be symlinked, or not symlinked, hard linked. And then when we construct the level scanner, and honestly, I think this is just like levels into iter map. And this is going to be level scanner. And actually, we can just do it like so. New. And then collect. And so that we need to implement new for this. And this is going to take a level. Okay, for now it does nothing, right? Okay, so let's go ahead and make that API on level, and then we can the question here in my mind is, do we do the hard linking in here or in the level scanner? I'm thinking it's the level scanner. So let's just give it a these are tree files. And this is going to return a vec of path buffs in order. So let's just do that. And so we'll have A, B, or C. And the question is, do we want to do that in A, B, C order or in C, B, A order? So the newer one is first. And I think it's C, B, A order. Order. So the older ones are at the end, right? Okay, so let's do some copy pasta here. So we'll do, and this is self.path, self.level. And then what we'll do is if cfile dot exists files dot push, and this should be a path buff, correct? Yes, it is. C file. Okay, and then we're gonna return files. We're gonna copy pasta that, and honestly, it's probably better to do this as a loop for file name or file base in CBA. Excuse me. And you may see that we are doing something here we could do a bit more functionally. Okay, so that's fairly clear. I don't need return files. Sorry, I've been tuned too much TypeScript and Go lately, poisoning my brain. Okay, so maybe what we could do instead is turn this into C. Let's take this. We'll do into iter flat map. And then we'll go self.path, self.level. Let's just rename this to prefix. That's easy. File dot exists, then file. What's wrong there? Unnecessarily closure with, oh, then, okay, what did I do? Okay, what is the signature of then? Oh. It's just saying use then some. Yeah, which is the right thing to do because we already construct it. We don't need to wrap a closure around it. Okay, so this is saying give me the C file, the B file, and then the A file. And give me all the ones that exist. So now we could look at, oh, is this, A or B or C? Do we have an open tree for it? But I think that this is simpler because what we want is the files anyway, so we can go ahead and hard link them. Yep. Okay. So now that we have the list of the files that this level owns, so to speak, we can go back to the level scanner and we can go we're gonna get we're gonna get tree a tree from these eventually. Um, but what we're going to start with is hard linking them. So let's do let's call it source files level dot tree files. Okay, and then we want to hard link. So let's see how we do that. Standard fs hard link. So we need to have a way to generate a name, and I'm thinking that there should be something in the scanner which is like it's I don't know, like unique identifier or something. Sorry, standard, what are we going to look for? Maybe there's something in standard OS. What is this? OS raw? No. No, this is all like, yeah, that's not what we want. Okay, so we're gonna need some kind of, maybe we just go get a crate that does this. Like I was thinking UUID, but that's like, oh, do I want to really bring UUIDs into this? Let's say like look for unique, not pointer unique. We don't care about that. Let's look for identifier. The other thing we could do is use a timestamp. Let's see if there's something in here for time. Not elixir. Time. There's standard time. Instant. Why don't we use this? The only potential problem with this is that you know, clock can go backwards, but we're really just using it for, can I identify this thing? It's like, I think that it would really depend on resolution. Okay, so here's a, so it does use a monotonic clock. So if we're doing this like in a tight loop for whatever dumb reason, if it's using a monotonic clock, we're guaranteed that that's going to be incremented the second time you call it, or every subsequent time you call it. So you get time. Right, so clock can be set and represents monotonic time since some unspecified starting point. That's good enough. We don't actually care what it is. So no crate needed. Cool. So we're going to use standard time instant. And here we're gonna we're just call ID is gonna be an instant. And this is gonna be instant now. Okay, and then here's the issue. Level scanner new is not going to be able to take just the level anymore. So Let's just go ID like so. And let's go ahead and pull this out because I think there's going to be a borrowing issue. Okay, so this is going to take level, and it's going to take, we're going to let it borrow ID. I think instant is probably copy, but let's look it up real quick. Interesting. It is not copy. Okay. Then the question becomes, can we format it into something? Or can we get... Oh, it does implement debug format. Okay. You can add durations to it. Maybe what we do is, we hash it? I want to get it to a stable string format. And I'm worried that debug is going to put like instant and then like brackets around it or something. So let's just read the source, honestly. So it wraps time instant. Right, this is not that surprising when so this internal time is an operating specific one, which is fine. Okay. Okay, so it just calls format on the internal one. So we could look at, for example, so it uses this internal create sys time. We need to know how this works. Rust, lang, rust. Now I could just make a little script and have it print out, like do instant and have it do debug and see what happens. But I like a little pain, so we're gonna go, sorry, it's in library. Standard and sys. Is that what we saw? Create sys time. Okay, this is the core crate, is it not? Not the standard crate. Nope. Let's create ops. Right. This might be a like a weirder overlay thing. Might be standard arch. Nope. Okay. So this is the file that we were looking at, right? And we're seeing this. It's this sys_time module that I'm looking for, which has the inner versions of it. But if I go into sys here, I don't get time. It's not there. Okay, let's just there's core time. Okay, so there's probably some compile time goop here. Let's look at that. Okay, so it's going to give us this tvsec, tvnsec on Unix. Ugh. I was hoping there was going to be something that would let us turn it into an integer, since now what we could do is pick here. Pick an instant which is is the only way you can construct these is with now. Duration sense. Okay, this might be too much of a rabbit hole. Let's look at what our other options are here. Oh, here. So this is a system time, units epoch. Can you get... can you convert this into an instant? It's non-monotonic, right? Of course, we expect that. But is there a method on it that lets you do... You know, that's great. Let's just use system time. Because I think that we can do this as a... We can get a duration from it. And then we can get, like, I don't know, as nanos or something like that, as millis, as micros, like, and then format that. I think that's what I'd like to do, because like we want a duration since a particular time. Instant is monotonic, so we're guaranteed not to get a rollback if we do it in a tight loop, like the clock going backwards or like leap seconds or whatever. But there's no equivalent to Unix epoch for instant. So yeah. All right. So this is going to be a U128 actually. System time and duration. Okay, so we're going to say this is system time now dot duration since system time Unix epoch. That's going to give us a Oh boy. Unwrap it. I don't care. We need like as what? Let's do as milliseconds or as nanos. Let's do as nanos. Okay, and then this takes a U128. That might not need to be borrowed, but okay. All this to say, we're going to use this to create some, like, do the hard linking, like format a file name, with this ID that is unique to this scan. Okay, we didn't need to import that directly. And then once we have that, we can open the trees for each of them. Maybe even the iterators for that. Yeah. Okay. So let's do. Okay. So we have, and this is a path buff. What we want to do is, and this needs to be mute because, no, it doesn't. We're going to create a new path buff. So let's say the new file is going to be source file. We need like the base name of it. Okay, let's do scan file. It's source file dot with extension. We're just going to change the extension to be, and we'll say scan ID. Make it insanely verbose. Yeah, and I think there's some bits here where we're gonna have to do results, because here, that needs to be a method. Okay. Needless borrow, fine. Okay. So then we need to do standard fs hard link from source file to scan file. Okay, and this is going to be have a result here. So yeah, I think this needs to be we're going to have to do result self here. And that means that we're going to have to do this is going to have to return result self. And this will have to return okay. So we're gonna have to go back up and start exporting. Yeah, like so. This is gonna be a result of impl iterator. Okay, crazy stuff. Oh, and this is not. This is vec level scanner. And it's going to need, yeah, I think I just need to do this. And we don't need to give the full thing here. We just need to do result of vec. I need one more? Yeah. So that comes out as vec of level scanner. Okay. All right. Okay, and then this can go question mark right there, right? So if we can't hard length the file, then we need to abort. And then the last bit of this needs to be we're going to make a vec of the trees that we want, and we're going to say tree from file scan file question mark, and then we'll do trees dot push. Okay, so we've got okay, well, we'll borrow it. Okay. So we're pushing things into here, and we're going to need right. So I think what we're going to need here is we'll need trees, but these are going to be a vec of peekable tree iterator, tree entry iterator, right? Okay, trees dot. Yeah, because like I could potentially do the thing here is that this tree entry iterator clones the tree because it's just a file and a trailer struct. So we could potentially do it right here. Yeah, let's just say okay trees, and let's do it here. Entries question mark peekable. Okay, so that gives us what we want in terms of the structure of each level. And remember, these are in reverse order, so we're always going to, in this scan for a single level, we're always going to pick the one that is the first. They're the newest. We'll pick the newest first, right? Okay. This is kind of a complicated feature. I think we're getting closer to the solution here, but yeah, that's fine. Let's just call it error. Okay, So the only problem I see potentially is that um, we need to do something with the nursery so it looks more like a peekable iterator. We could, yeah, let's not worry about that right now. Because I think that this is potentially harder, and once we understand how to do this, then adding that is like, oh, well, we're doing it in RAM now, so it's easier. Okay, so what do we want the behavior to be on each level? Um, we have the tree iterators in order, from newest to oldest. So what we want to do, I think, is let's kind of outline this in some comments. So we want to, our goal is to find the lexically is not the right word because we're operating on bytes, but find the smallest, let's do it like that, smallest key that is not deleted, right? That's the overall goal for each call to next. So what do we need to do? We need to, peek all the all of the iterators. We'll say all of the trees. And then we need to and there's only 3 at max. This is the part that's making me think, oh gosh, I'm gonna over engineer this with a bunch of loops. Um, so let's outline some of the scenarios. So you might have, let's just say there's, if we've peaked all the trees, let's say there's key A and key B and key C. Those are disjoint. Of course, this is newest to oldest in order. And let me just move that up here, right? So this would say what you should return is A, and you want to consume the iterator on first tree. Okay, so this is a really simple scenario. Now, this is a parallel to, let's say you have B and then A and then C. Again, you'll return A and then you consume iterator on the second. And why is this valid? Because this is saying that, this, you've already passed A on this newest one, which basically says it doesn't contain that if you're iterating in order, which we are on each one. If it's if this is, you know, the newest file there, and it has no A, then we know that the A here is what we want to return. Okay, and then the same would be the for this. So like if the A was here and this was like B or C, then we would want to consume the iterator on the third. So now we get into what happens if there are conflicts. So let's just say they're all A's. And we return the first one, and then we consume the iterator on all of them, right? Because we know that this is the newest file. This is, so that's the value we want to return. And so we return that. If it's more like B, A, then we want to do return A from 2, and then we consume iterator on 2 and 3, right? Now, we need to handle the possibility that there's a tombstone. So if it's AX, A, then what we want to do is we don't want to return anything. We want to loop, right? Because this is saying the newest file was deleted, or the newest file has a tombstone in it. Consume all. And when I say consume iterator, I'm like, we're starting with peak, and then I just want to do next on them, right? And throw out the result. Okay, and then if we have something like this, so you can see there's kind of 2 levels here of, here again we want to loop, consume iterator on 2 and 3, right? So then this will advance these, while this one didn't get advanced because it has a greater, like a larger key, a greater key than this A. Okay. So let's talk about a different problem. Okay, so let's just, that's the basic ordering things. Here's the basic tombstone things. Let's talk about ordering and tombstones. So let's say you have BX and A and A. Well, we want to return A2 on 2 and 3, like so. So, you know, the key still needs to be the smallest one. And of course, if it's like, you know, BX, A, then, you know, we return A3. That's an interesting case on 3. And then on the next time around, it'll probably be, oh, well, these two are equal, assuming that there's nothing between A and B. There's no like AA or anything like that. I'm using the X here to mean it's deleted, right? I could use like negative or something like that. Okay, so I think we're going to need, this is like sort of a fold or a, you know, reduce type algorithm with an initial condition of the first key in the newest file. So I think what we want to do is go first keys, let's collect the first keys for all of them. So we're going to do and is this tree entry iterator? I want to make sure that's the correct thing. Yeah, loop over all entry. Yeah, okay. And the items are entries, right? Okay. And I think that right. So this does the traversal of the tree. Like we're not going to get poslin entries returned from this, but we could get we could get tombstones. We could get deleted key entries. Okay, so I'm going to go with let's do self dot trees iter. We're going to map that into peak. Yeah. Oh, we also need to handle the case where there's nothing and then like A and A. So like that iterator is consumed. Then we return A2 and consume iterator on 3. Now the other thing we could do is like when an iterator is empty, we drop it from the vec of trees. That, and as long as we're yeah, I think that's something that we could do as an optimization. Drop empty iterators question mark. Okay, so we're going to do peak, and then we're going to map that if it has an entry, right? We're going to get the key. Okay, so this is going to be we're going to get a vec from that. That's going to be a vec of option of U8s. And I think we need to go ahead and clone there. Well, no, we'll clone when we get the actual entry, right? Okay, so I'm going to need iter mute because peak requires mutating the iterator, right? Like it's got to consume one and then hold on to it, right? Such that when you call next, it like gives you that and then throws away its internal state of what it peaked. Okay. So now, okay, so we know what the keys are. The first key for each file that we've been iterating. So we kind of have this two-phase thing. We need to find... I think it comes down to what's the index of the smallest key, right? So we need to find that. I think that's what we want to do. So let's call this smallest key index, right? And then let's see. This is going to be kind of complicated. This is going to be a usize, by the way. We're not going to collect. We want to. So we're mapping each of these iterators to its first key, and then we want to do like min by, or no, we want to do enumerate, because that gives us the index, and then we'll do min by, or we want min by key. Yeah, min by key. The problem here is that right, so we want to do min by because we want to compare them. Right, so this takes an item and an item. So this takes A and B. And A and B, so the item there is a tuple with a usize and then an option. I'm going to do this the dumb way first. A.1, B.1. And we're going to say if this is none, none, we don't actually care. What does this need to return? We're going to just return an ordering. Ordering equal. Let's look at the definition of this. It turns the element that gives the let's, I think option has partial equal on it. And I think that, or partial ord, I want to see what so it's like left compared to right. Okay, so if we want min by, so we want none to be the greatest value, because we always want to get a key as the min value, not a none. Now, if we get none, well, it actually doesn't matter at that point. We'll figure that out later. So if we get some and none, we want to get ordering here. Let's do that. Import that. Use. Okay. We want ordering less. If we have the inverse, none, some, we want ordering greater. And if we have anything else, then the ordering on, So min by has to return an ordering. Partial, we need comp. Yeah, so anything else, we're going to do a.1 comp b.1. And that's not going to work. Yeah, so, and here, we still, this is like really complaining. Yeah, it's... So I think it's going to be option usize, because now we're going to do... So min by returns an option, and map, we know that we have, you know, a tuple there. We want to return that. Okay, so what's the problem here? Okay, so we just need to borrow Lexo. Okay, so that was complicated. Let's review really quick what we did. What we want to find is the first iterator. So like, we want to find the iterator that has the smallest key, but is the first one. So I'm assuming that, yeah, so if several elements are equally minimum, the first element is returned. The iterator is empty, none is returned. Okay, so if they're all equal, then we can return the value of the first iterator and call next on the others, right? If they're not equal, then we'll get the first index, which is the lowest. Okay, so I think we still need the keys too. So I'm going to break this out into let we're going to take the first part of this, collect, and this is going to be, you know, a vec of something. And then we're going to go, this is keys and indexes dot iter dot min by. Okay, what's wrong there? I think we need to clone. That's not the problem, but I do think we need to clone. Okay. Right, so this is, why does it still think it's a, so this returns option U8, this clone here should, Make that a vec of U8. All right, that's not even the problem. What is the problem? Okay, expected standard option. Okay, we need a star I there. Okay, that was the issue. Remember, this usize is copy, so like dereferencing it is fine. Okay. Okay, so now we have the keys in their indexes. We have the smallest key index. So we know that we know which one is the one we want to consume. If it exists. So I think I almost feel like I should do there's going to be one, right? Because it always picks the first one, and this is never going to be empty. As long as we have some trees, I mean, there's a possibility that there's no trees, right? In which case, okay, if self.trees is empty, oops, let's handle that case. Return none. If there are no trees in this level, don't do anything. Right? Because it didn't construct them in the constructor, so we might as well like not return anything. We know that there's nothing here, so we don't have to go by this. And then here, I know that there's at least one, so I can say I can put an expect here. I think this is a fine place to panic. There were, or we could just say no trees to scan, and level, and it actually doesn't matter because we're not holding on to it. Okay, so now we know, like, hey, it's one of these, right? It would be kind of silly to have this iterate over this empty vec producing nothing. And then be like, oh, well, your index is, none. And now you got a match on it. Well, I would rather say if there's no trees, just abort early. I think that's reasonable. Okay, so now let's think about these cases. So if I think we want to take a slice of keys and indexes. From the smallest key index to the end. Yeah. So let's do okay, so this is going to be really dumbly named. We'll fix and we'll get a better name for it. We'll say iterators to check. This is going to be keys and indexes. We're going to do, I could run into some crazy borrowing here, but double borrows of double references of things. We're going to take smallest key index to the end. Okay. So this is saying we've determined that the you know the freshest file with the smallest key is the first one in this slice. Which means that I'm trying to pull out the pattern here. The pattern is we need to match on iterators to check. We don't need to borrow that. We actually need to consume it. I want to say 0. I'm concerned about that being unchecked. Right. So we know if this is none, then all of them are none. Right, because we made sure that this was the greatest value in that partial ordering. Which means we have no more to do. So we return none. Yeah, I don't know that. We really only got this smallest index in order to slice this collection. Let me outline a little bit more. So I want to consume the first iterator as the return value, right? Because we know it's freshest and the smallest key. And then I want to loop through the rest of the iterators. Consuming them if they are the same key. I mean, you basically just want to advance it, go like, hey, that was an old value, we need to toss it out, right? We need to get rid of it, because this fresher value, like we got two things going on here. One is what's the smallest key, and one is what's the freshest. And we want the smallest key with the freshest. And anything that's not the smallest, we just let stay. Anything that's not fresh, we need to toss, so that we can make sure that we consume all the right stuff. Okay. So maybe it's not shaped like this. Okay. So the other thing is, let's call match result. Maybe let's put that on hold, because I think that what we can probably do is do like smallest key index plus 1 ... keys and indexes .len for the iterator for the rest. So let's just get the result. So we want to match on um, self trees smallest key index next. Okay. Right, fine. None. So this is, again, the empty thing. If there are... We want to return none. We want to return early. If it's some, and here's where we can use pattern matching. And I knew there was going to be an internal loop. Okay, so we need to import entry. Use create entry. Okay, so we know that this is an entry. So if it's an entry deleted, and we only care about the key. This will be, we need some kind of thing where we need to know we need to do basically here loop this loop through the iterators, rest of the iterators, and consume this key. And then we do continue, right? Because we need to do a loop here. So I'm going to do loop. I'm going to put all of this inside this loop. And we're almost out of time. I'm sorry, I have a hard stop today. We need to handle this other case, which is not a tombstone. Actually, this is the happy path case, right? So if we have key value and we're not considering timestamps, we'll eventually do that. I think that would be fun as a future episode. So here we know that what we want is we want the key and the value. And if it's anything, if it's any other thing, then we need to do unreachable. We need to panic here. And we'll say tree iterator emitted poslen, entry poslen. Okay. It is very unhappy with this piece of code. I might, how do I turn that off? We'll fix it later. Yeah, so unfortunately for each of these, we need to distinguish between these things because we still need to consume all the iterators that use this key. So maybe we make a little, I don't know, a little closure that we can call in both places to iterate through those. The other option is that we just copy pasta the code. That's probably what we'll do next time. And again, thank you for coming this time. We will wrap this up next week, and I hope you have a good Sunday.